evening, everyone. I am Renu Raman Saho, and today we'll be discussing about some of the assignments of electronic theory of solids of the previous year. These sample questions will help you solve the assignments which are given in the assignments of this year. So we'll get started. The first question that you have is the number density n of electrons is given, and you have to calculate the mean drift velocity Vd of an electron through a wire when the current is 1.4 ampere passing through it. So what are the given data? So you have been given the number density n, which is equal to 8.5 into 10 to the power 28 per meter cube. You have to calculate the drift velocity, so this is what you need to calculate. Okay, and the current you have been given, current is equal to 1.4 ampere, and you have been given the cross-sectional area A of the copper wire. It is 7.85 into 10 to the power minus 7 meter square. So now note that all these units are in the SI units. So whatever the formula that you will be using, the answer that we will get is in SI units as well. So I hope you know this formula. J is equal to NeVd, where N is equal to the number density of electrons, E is the electronic charge, which is nothing but 1.6 into 10 to the power minus 19 coulomb, and J is the current density. J is the current density. So now what you have to do is, and this is given, what is how is it given? It is given by I over A. Okay, so so why this so now using this formula, what you can do, just keep this slide. So J by A, J is equal to I over A, and this thing equal to NeVd. Okay, so I you have been given is, how much is I? It is 1.4. So we have to calculate the drift velocity Vd. It is I over A and E. So now you just put the values, 1.4 ampere, and A is 7.85 into 10 to the power minus 7 into number density is 8.5 into 10 to the power 28 into electronic charge 1.6 into 10 to the power minus 19, and this thing will give you your answer. It will come out to be 0.131 into 10 to the power minus 3 meter per second. Okay, so I hope you understand this formula. J is equal to NeVd. Why this comes up? So there is a so let us spend some time to discuss why this is the formula, or a heuristic derivation of this formula. So let us consider first, so we are given a wire. So you are given a wire of, let's say, cross section A, and some amount of, so this is some metallic wire, okay, and this is some distance dx, and some charge dq, let's say dq is the charge which is passing through this distance dx, uh, passes through dx in time dt. Okay. Oh, so we have this charge. This is a metallic uh, conductor, cross section area A, and we are talking about a small distance dx. Okay. So the current will be and this distance is passed by that uh, yeah. So the current will be given by dq over dt. Uh, so this dq amount of charge is passing through this cross section in time dt. Now, what will be this dq? It is the charge present in this amount of volume. So, what is that charge? So, the charge is the number of electrons. The number of electrons will be the number density of the electrons. So, this is Ne. So, N is the number density of the electrons, and if you multiply it with E, then it will give the density of the charge. And now this thing will be what? Ne and the volume. So, volume of this thing will be dx times A. Okay. So, what is this? If you just put this over here, what you get is NEA dx over dt. So, this dx by dt is your the drift NEAVD. Okay, and if you take I over A, this thing will be NEVD. So I over A, this thing is nothing but your current density. Okay, so this is the formula that we used to solve the previous problem. So now we can go ahead to the next problem. So the next problem, it asks, it is about the thermal conductivity of copper at 300 K. So you are given the thermal conductivity. So thermal conductivity of copper, it is given at 300 K, and it is 376 watt per meter per Kelvin square. And if the average time between the collisions of electron, it is given. So if you have done the Drude model, then there is in the Drude model there is a parameter tau. So this is the time it is talking about, the average time between the collision of the electrons in the copper. This is given, and this is 2.3 into 10 to the power minus 14 seconds. The Weidemann Franz, so it is asking the Weidemann Franz constant, CWF, and you have been given the thermal conductivity kappa. Thermal conductivity kappa is given, it is given as 376 watt per meter per Kelvin square, and it is at temperature is 300 Kelvin. Okay. And what you have been given is the number density of the N is equal to 8.38. This is the number density of electrons into 10 to the power 28 per meter cube. And just a second. So you have been given thermal conductivity, and so what is thermal conductivity at temperature T equal to 300 Kelvin? You have been given the number density, and you have been given this is the mass of the atomic mass of the copper nucleus, and electronic charge you have been given 1.6 into 10 to the power minus 9 coulomb. Okay, so it is actually some mistake in the question, so it is 10 to the power minus 19 coulomb. Okay, so how do we? So we have to use the Weidemann. We have to find the Weidemann Franz constant. So let us see what is Weidemann Franz law tells. So what it tells is, if we have the thermal conductivity kappa, and we have sigma the electrical conductivity. And this is thermal conductivity. And this thing is given as this is directly proportional to, this was first experimentally determined that this was proportional to temperature, and the constant of this proportionality is your Weidemann Franz constant. So this is your Weidemann Franz law, and the constant of proportionality for this is your that is your Weidemann Franz constant. So let us first understand how this thermal conductivity and electrical conductivity are related. So what is thermal conductivity? This thing is nothing but this is just a parallel to understand why this is important why this is an important law. So kappa is, so we know that sigma is the conductivity. Okay, and this is defined as, so this is electrical conductivity. So this is defined as J is equal to sigma E, or E if you just write it as minus of grad V, or if you consider in one dimension it is dV over dx. So this is a potential difference, and what is J? J is nothing but the I over A, and I is nothing but the charge over time. What is the charge passing per unit area per unit time is equal to sigma, and this is, you have a dV over dx. So this is, so the electrical conductivity is the electrical charge passing per unit area per unit time, and it is proportional to the gradient of the potential. Similarly, if we define the same thing for heat, so Q heat, the amount of heat, so this heat is measured in joule. Okay, heat per unit area per unit time, this thing is proportional to the temperature difference now. So this is proportional to dt over dx in one dimension, and the constant of proportionality is nothing but your thermal conductivity. Q heat over dA is equal to kappa dt over dx. So now we have from Drude model, so the Weidemann Franz, so this is just an analogy to understand the thermal conductivity and the electrical conductivity. Now what? So now let us come to the problem. So the problem is asking about finding the Weidemann Franz constant. So kappa over sigma. So kappa you are already given is equal to. So this was proportional to the temperature. So this will be CWF, the constant of Weidemann Franz, times temperature. So this will be nothing but CWF is equal to kappa over sigma into T. So what is sigma from Drude model? It is from Drude theory. Sigma is n a square tau over m. Okay. Where now what is this mass? This mass is the mass of the free electrons. So Drude theory is about the classical free electrons. So this is the mass of free electrons. So this implies CWF is equal to kappa over n e square tau over m into temperature. Now you see all these values are given. So kappa is equal to 376 in SI units. The mass is, see, this mass is the mass of electrons. In the question you have been given the mass of atomic mass of copper, which is actually a data which is not needed. So you have to put here the mass of electrons 9.1 into 10 to the power minus 31 kg over n. So the number density you have been given, it is 8.38 into 10 to the power 28 into e square is 1.6 into 10 to the power minus 19 whole square, and tau is 2.3 into 10 to the power minus 14, and temperature is 300 Kelvin. So, and when you calculate this, the quantity you get is 0.231 into 10 to the power minus 7 watt omega per ohm per Kelvin square. So this is your answer. This is your Weidemann Franz constant. So what this tells you is that the thermal conductivity increases as the with increase in the temperature, the thermal conductivity increases with the electrical conductivity. What it also means is that the good thermal conductors are good electrical conductors. Now let us come to the next question. So it is talking about it is asking what is the value of plasma frequency of a material in hertz. It is given as 5.7 into 10, some value of plasma frequency is given, and another value of two values of plasma frequencies are given, and the plasma frequency changes from 5.7 into 10 to the power 15 to 5.7 into 10 to the power 14 when the number density of a free electron gas changes from N1 to N2, and we have to find what is the ratio of N2 to N1. So what I will do here, I will just give a general argument of how you should look at, so how you can get the plasma frequency and what are the quantities it depends on. Okay, and then I will give you the formula, and you can calculate for other problems as well of the similar type. So so we want to find, so let us consider, so we want to find something called plasma frequency. Let us denote plasma frequency as omega p. Okay, plasma frequency. We have to first consider a electron gas. So let us say that there is some electron gas all around, and we just consider a small volume like this. So so in this volume, in this rectangular or like cuboidal volume, there is free electrons which are there, and the electrons are free to oscillate or free to move. So this you can think of it as like there are since it is a metallic volume, so there are some plus charges and minus charges. As a whole, this is neutral, but the electrons are free to move. They are like classical gas, and let us say at some instant of time, this has moved delta S towards the right. I mean the electron gas, it has moved somewhere outside. So somewhere this side, and this area we got some positive. Okay, so and this delta S is really very small. So now what will happen is you will have a field which is going from plus to minus, some electric field E, and in that electric field, if you consider some electron inside, that electron will feel a force. That force so this electric field, so you can think of this system as a parallel plate capacitor, and the electric field will be E is equal to sigma over epsilon naught, where now this sigma is actually the charge density, surface charge density. Okay, now what will be this surface charge density? Let's say that this metal has n as the number density of electrons, number density of electrons. So the charge in this small volume, this will be we want to find the surface charge density, or it is the charge per unit area charge per unit area in this thing, in this particular plate. So this will be given by, let's say, the number density n, and let's say that this has a cross section area A, and n, and so this is the number density of the electron. If we multiply with E, it will be charge density of the electron. So it is n E, this is the charge density, and if I multiply it with the volume will be delta S times A of this particular volume, delta S times A. And so this is the charge in this spreaded along this area, and now I want to find per unit area is this. So this area will cancel this area, so what we will have is n E delta S. This is sigma, this surface charge density is this much. So the electric field E, which is inside this E, it will have a magnitude of n E delta S over epsilon naught. So this is the electric field, or the magnitude of the electric field is this much. And if we consider the direction, let's say this is positive x direction, so electric field will be this much, x cap. Now what will be the force on the electron? Force on this electron will be force F is equal to minus E times E. The force will be along this direction, so this will be minus E, and this electric field you can take from here, so it n E delta S over epsilon naught. And so basically what you get is, and this is the direction will be minus of x cap, so the force is this direction, and this thing is nothing but n E square by epsilon naught into delta S x cap. So now you see the force, this force can be written as what? The force can be written as mass times acceleration. So the displacement of, so this actually the bulk of all these electrons are moving it is moving due to this electric field. So it will be the mass of the electron. So the force will be mass times acceleration. Acceleration will be given by d2 delta S over dt square, or so the force, which is nothing but m d2 delta S over dt square, is equal to n E square minus x cap delta S over epsilon naught. So now you see, and the force, so this is along x cap, the force along the x direction is this much. So if we cancel out, if we take the x component of the force, what we have is d2 delta S over dt square is equal to minus n E square over m epsilon naught delta S. So this you can recognize this is a equation for oscillator, equation for oscillator, and and this is actually the oscillation of the electrons in that metallic volume, and this thing you can compare it with d2s by dt square, and this is omega square delta s. From here you know that omega p whole square, so you have to compare this. This is given as n e square over m epsilon naught. But what is n? So here what did you get? Omega p is equal to, so omega p is a frequency, it has to be like positive. So n e square over m epsilon naught. What you get is omega p is directly proportional to, say, E is a constant, the mass of the electron is a constant, and epsilon naught is a permittivity of the electron, which is also a constant. So the omega p, or the plasma frequency is directly proportional to the square root of number density of electrons. So you can use this formula to solve the problems of, like, if the plasma frequency changes from a particular value to another particular value, how the number density will change. So you have to just use this proportionality and solve the problems. Now let us go to the next question. So here you have been given a free electron gas in 2 dimension and the relation between the electronic density n and the Fermi vector kf. So to solve this problem you have to understand how we get this electronic density n in a particular dimension. So this is the one of the question in your current assignment. So what I will do is I will give a general outline of the derivation. How do you calculate the number density, like in any arbitrary direction? So what I will tell you is how to calculate, how to compute the electronic density n in any let's say in 3 dimension, and you can generalize it to 2 dimension or any other lower dimension, and then you can find this yourself. So this is one of the question in your current assignment, so I am not going to solve this directly, so but I will give you this technique how to actually compute this. So the first thing we have to do is we have to count the number of, so let us consider, so basically we have to count the number of electrons, in a metallic volume. So how do we do that? So before counting the number of electrons in a metallic volume, the approach we do is we count the number of states in the metallic volume and multiply it with the probability that the states are occupied. This will give you what is the number of electrons in that metallic volume. So how do you do this? So basically so this is a very general technique. We consider a metallic volume, let's say a cubic volume. This is a cubic volume and it has a length L, so L along all the sides. Consider a cubic So the electrons are free in the metallic volume. What it means is that the electron feel no potential in this volume of length L. So let us look at just one of the direction, and then we can understand how do we count the number of states. So consider this along x, this is x and this is the origin 0 and L. So in this metallic volume along one direction, the electron can be so the states of the electron, if you solve quantum mechanics, it will be given as psi n equal to 2 over L sin n pi x over L. So this comes from the quantum mechanics. Another way to look at it is, so this is what so this is the wave function of the electron, wave function of electron, and n, this n equal to 1 2 3, this determine what is the state of the electron. And for example n equal to 1, so n equal to 1 means you will just get psi 1 equal to 2 over L sin pi x over L. Okay, so what you get is just this 0 to L. Okay, and the important thing to note is that it is actually the psi 1 mod square which will give you the real physical state, the physical quantity, which is the probability density of finding the electrons, So what it means is that if you had taken, let's say this n, we are saying that it is positive 1 2 3 and so on. If we do n is equal to, let's say, minus 1 minus 2 and so on minus 3, what you will get is let's say, for example, consider n equal to 1 and n equal to 2. So n equal to 1 n equal to 1 and n equal to minus 1. So for n equal to 1 you will get this state, n equal to minus 1 you will get this state 0 to L. But when you, so these two states are not distinct, these two are actually the same state, because what is the physical quantity is your psi 1 mod square. So when you do the mod square, you will get the probability density of finding the electrons as this 0 to L. So we shouldn't have to distinguish between n equal to 1 and n equal to 2, and so these two are, n equal to 1 and 2 are not the distinct states. So whenever we are counting the number of states, similarly n equal to 2 and n equal to minus 2, these are not the distinct states. So this is same as this. So whenever we are counting the states, we have to take only the positive part, and in case we are counting from minus 1 minus 2, if we are just counting for the sake of some mathematical ease, then we have to remember that we are double counting the states. Okay, so now with this in mind, we will count the number of states. So there is a technique to count the number of states which is quite easily visualizable. So let us consider, so 0 to L. So for example, the lowest energy state will be this. So, and here you see this is half the wavelength of the, so if you can imagine this L is equal to lambda by 2. So half the wavelength of the electron wave function. So now if you have this is the ground state. So you go to the next excited state. The next excited state will be 0 to L. So here L is what? L is equal to just lambda, which is nothing but 2 times lambda by 2. This you can write as 1 times lambda by 2. Then what you have is So the next excited state. So why we are doing this? Because we want to count the number of states, and from there we will count the number of electrons. So from 0 to L, you see, now there are three uh, so there are three half wavelengths. So here L is equal to 3 lambda by 2. Now you see, as we excite the electrons, what we are getting is like 1 lambda by 2, 2 lambda by 2, 3 lambda by 2. For higher states, let's say somewhere here, so we'll have a very high lot of states. So 0 to L. So how many half wavelengths? 1, 2, 3, 4, 5, 6, 7. So here L is equal to 7 lambda by 2. Similarly, in general, what you can do is what you can do is in general, L is equal to n times lambda by 2, where n is actually, you see, n, what was n equal to 1? This was the ground state. N equal to 2, it is the first excited state. The n is actually counting the number of states. Okay, so now let us use the de Broglie principle. So lambda is equal to h over p. Okay, and or you have this wave number k equals 2 pi over lambda. So if you use this so from here you get lambda equals 2 pi over k, then what you get is L is equal to n over 2 and lambda equal to 2 pi over k. So basically what you get is, so this pi 2 cancels, so n pi over k. K you get as n pi over L. Okay, or alternatively n is equal to L over pi into k. Now if you want to find let's say at very say n is positive, n is always 0, 1, n is 1, 2, 3, so on. That is why k is positive. And if you are to consider the negative k, then you are actually double counting the states, because the positive and negative numbers, these are the same states. So now let us count the number of states. So to count the number of states, what we do, so let's say n, we keep the subscript L, L is the level or the state. This thing will be given as, so now we have to say, we got L is equal to n lambda over 2, k equals 2 pi over lambda. So this n. So this we derived along the x direction. Along x direction. So that is why we can write, let's say, kx and nx. Similarly, for ny will be L ky over pi, and nz will be L kz over pi. Okay. Now we want to find the number of states. So let us imagine we want to plot this in the k space. So here kx, ky and kz. Or equivalently you can have, so it is just a matter of some constant nx, ny and nz. So what you will have is a lot of states which are on this positive kx and ky. So you remember that it has to be positive. Okay. Similarly, in nx also you will have lot of positive kx, ky and kz. So now we'll consider a uh, small volume in the K space, or equivalently in the space of this n, or the number of states. So what we have to do in the positive, in the octant, in the first octant, we have to take d and x, d and y, d and z. So we want to count the number of states. So this is d and x, d and y, and d and z. Small volume here, and we have to integrate over the first octant. First octant. What it means is 0 to infinity d and x, 0 to infinity d and y, 0 to infinity d and z. So this is how you count the number of states. So now if you want to, so this is the number of states in 3 dimension. In 3 dimension. If you want to find the number of states in a 2D system, in a 2D system, what you will do? You have to, let's say the 2D system is in only xy plane. So you have to do d and x 0 to infinity, d and y 0 to infinity. Okay, so this is for 2D system. Okay, so this is what you have to do for your problem. Okay, for the problem which is given which we are discussing right now. So we have to find the 2D states. So now what we have to do, so let us go ahead with this. So the number of states and L will be given by 0 to infinity, 0 to infinity. So instead of d and x, d and x, d and y, d and z, we will use this formula. From here we'll get d and x is equal to L over pi d k y. Similarly here d and y is d k x, L over pi d k y, and d and z is equal to L over pi d k z. So what you will have is 0 to infinity L over pi d k x, integral 0 to infinity L over pi d k y, 0 to infinity L over pi d k z. For if it were a 2D system, then you have to just use only these two integrals. Now what we will do is, we have the number of states as 0 to infinity L over pi dkx, 0 to infinity L over pi dky, 0 to infinity L over pi dkz. Okay, so we have taken kx to from 0 to infinity. Why? Because we want only the positive. Now here comes an important thing. So if I consider the negative k values as well, L over pi dky, dkx. So if I take the negative values as well, so I am actually double counting the states. How am I double counting the states? Because I have taken the positive k value and the negative k value as well. But these two are the same. So this is equivalent to this. So that is why I am actually double counting. So I have to divide it by a factor 2. So now this will balance the extra count that we did because we increased the limit. So that is why we get this factor of 2 here. So now what we are going to do, minus infinity to infinity. So similarly for ky and kz. So 2 pi dky minus infinity to infinity L over 2 pi dkz. So what we get here is so L over 2 pi whole cube dkx dky dkz, and this is from 0 to infinity, minus infinity to infinity and minus infinity to infinity. So now you see this thing is in Cartesian coordinate system. Cartesian coordinate system. what we are going to do now, let us change the coordinate system to uh, spherical coordinate system. Spherical coordinate system. Here we'll define a quantity k as kx square plus ky square plus kz square 1 by 2. So what we'll have is n, the number of states l, number of levels l over 2 pi whole cube, and here, so in the Cartesian coordinate system we have to think of as from k to k plus dk. If we do so, this element, it will become as 4 pi k square dk, 0 to infinity now. Okay, so now what we have a very important thing. So in terms of k, we have, so l over 2 pi whole cube, 0 to infinity, 4 pi k square dk. So this thing can be written as g of so here we can see that there is a function of k, and it is integrated over all the k values. So this thing is called, so now what we have to do, use the dispersion relation. E is equal to h bar square k square over 2m. What this will give me is, so the number of states equal to l by 2 pi whole cube, 0 to infinity, 4 pi k square dk. E is equal to, now this is the dispersion relation, h bar square k square over 2m. Now what we can do, h bar square, so dE will be equal to h bar square k dk over m, and here if we just replace this, what we have is l by 2 pi whole cube, 0 to infinity, 4 pi k square will be 2me over h bar square, so 2me over h bar square 1 by 2, and dk will be 1 by 2, and this will be So what we have now is, so L cube we can write as V volume. So what we have, and L is equal to volume over 2 pi whole cube, 0 to infinity, 4 pi. So here we can write 2m over h bar square. So I can do this, 2m over h bar square, 3 over 2, and square root E dE. Now if you had a two-dimensional system, so this is for 3D. What you would have done here, it would have been L over 2 pi whole square, 0 to infinity. So this would have been 2 pi k dk, okay, for 2D. And for 1D it would have been L by 2 pi and dk. Okay, so now what we'll do is, so we have obtained this one, and this is the number of states over 2. This is the number of states. We have to find the number of states, and we have to multiply another factor 2, which comes for the spin. Every k state will have a spin degeneracy of 2. Here, if we write it as we can write this as n by L over V is equal to G of E dE. And on comparing, what we get is G of E is equal to, so on simplifying, we'll get m square 3/2. Okay, so this is the density of states, the number of states per unit volume from energy E to E plus T. Number of states per unit volume from E to E plus dE. So number of states per unit volume from E to E plus dE we have calculated. Now we can find what is the number of electrons. So the number of electrons, the way we have to find is, we have to use something called the occupation function. So we have the density of states GE 1 over 2 pi square 2m over h bar square 3/2 square root of E. Now we have to use, so this is density of states. To find the density of electrons, what we do, we have to multiply it with the occupation probability. Occupation probability. So it is given as f of E is equal to 1 over e to the power E minus EF over kBT plus 1. So here EF is called the Fermi energy, and Kb is the Boltzmann constant. So these functions looks like, so since it is a probability, it will be always less than 1, and so f of E is always, it is, so at some finite temperature T greater than 0, it smoothly comes to 0, and at T equal to 0, it is just an abrupt change from 1 to 0, and this change occurs at e to the EF, which is the Fermi energy. What it tells you is that all the states below EF are filled and all the states over EF are unfilled, or these are empty. So if we want to count what is the number of electrons, or the number density of electrons, so what you have to do is you have to calculate for, like, let's from energy E to E plus dE, what are the number of states available and what is the probability that these states are occupied. So we have to multiply with f of E. So this will give you the number density of the electrons, and you have to integrate over all the energies. So this will give me the number density of electrons. So n is equal to n electrons over V. So this G of E you can find for 2D case, for 3D case, for 1D case as well. So if it is, the question is asking you what is the electron density for the 2D case, then you have to use the density of states for the 2D. If it is the 3D metallic, if the question is regarding the 3D metallic volume, then you have to use the density of states for 3D. Okay, so this we have derived for the 3D case, but the technique following the technique that I told you, you can do it similarly for the 2D case as well, 2D or 1D case. So now let us find what is the number of electrons, 0 to infinity dE GE Fe, for at T equal to absolute 0, or at 0 Kelvin. So you see this function f of E at T equal to 0 is nothing but 1 when energy is less than EF, and 0 when E is greater than EF. So at t equal to 0. So now what we will do, so the number density of electrons and electrons over V is 0 to infinity dE, GE and FE. So at t equal to 0, Fe equal to 1 for E less than EF and 0 for E greater than EF. So what we can do is we can split the integral 0 to infinity dE GE Fe as two integrals 0 to EF dE GE Fe plus EF to infinity dE GE Fe. Now we use this. So when E is greater than EF, so f of E is equal to 0. So this integral vanishes. And when it is the value of E is from 0 to EF, so f of E is equal to 1. So what we have is 0 to EF dE GE and f of E is equal to 1. We don't have to do anything, and this so 1 plus 0. So basically we have the number density of electron at 0 Kelvin is equal to 0 to EF dE GE. Now we put the expression for GE 0 to EF. So the expression for GE is 1 over 2 pi square. GE is 2m over h whole square 3 by 2 square root of E. And when we calculate this value, what we will get is, so it is square root of E, so we can take all the constants out. 1 over 2 pi square 2m over h bar square 3 by 2 and EF to the power 3 by 2 over 3 by 2. So this 2 will cancel 2, and what we are left with is 1 over 3 pi square h bar square. So n is equal to 1 over 3 pi square 2m over h bar square 3 by 2 and EF to the power 3 by 2. This EF is the Fermi energy. So now if we invert this, so EF is equal to h bar square over 2m and 3 pi square n to the power 2 by 3. So this is the expression for Fermi energy in terms of the number density of electrons. So we got EF is equal to the Fermi energy is h bar square over 2m and 3 pi square n by 3. Now we can compare, so this is Fermi energy. Here we got an important formula. EF is directly proportional to n to the power 2 by 3. So the type of question that can come is how will the Fermi energy change when the number density is changed by a factor of 2 or 3. So this type of problems you can solve now. Another type of problem, and remember that this is in 3D. Okay, this expression is for 3D. You can find similar expressions for 2D and 1D as well. So now we will we can get something called the Fermi wave vector or the Fermi momentum. So Fermi momentum or wave vector, it is h cross kf or wave vector. It is Kf. So it is defined as Ef equal to h bar square Kf square over 2m. And from here, if you compare these two expression, Kf will be nothing but 3 pi square n to the power 1 over 3. Here you see Kf is directly proportional to n to the power 1 by 3. So this is another important relation you can use if some question comes up. So there is another quantity called Fermi temperature. Fermi temperature. So Fermi temperature is defined as Ef is equal to kBTF. Yeah. So Fermi temperature is defined as Tf, defined like this. So Tf or the Fermi temperature is Ef over Kb. Kb is the Boltzmann constant. And there is something called Fermi velocity also. Fermi velocity. Fermi velocity is defined. So sometimes the question may ask, what is the Fermi temperature of like if you will be given some number density n of the electron, number density n, and it can ask you what is the Fermi temperature. So and there is something called Fermi velocity. Vf half m Vf square is equal to Ef, and so basically Vf equal to 2 Ef over m to the power 1 by 2. So these are important quantities. Now you can and it all of this comes from this formula. Ef is equal to h bar square over 2m and 3 pi square n to the power 2 by 3. So if you remember this formula, you can calculate all other formula by your own. Like always remember that this is in 3D. You can do so for 2D and 1D as well. This you can derive. Yeah. So what we have done here is we have defined the Fermi energy in terms of, if someone asks you how is the wave vector related to, this is the Fermi wave vector, how is the wave vector Kf related to the number density n? So what you can do, so E equal to h bar square Kf square over 2m is equal to, so basically here you can use this formula. So what was the question that we were discussing was this: how n is related to Kf? How n is related to Kf? So this what I derived was like I did for 3D, but using the similar method you can do for 2D. So the key is to understand at this particular step of the derivation, you have to just use dnx and dny for taking the 2D system, and you can solve by the similar procedure which I explained here. So now let us go to the next question. You are all understanding, right? You can stop me if you have any doubt in the derivation. So now, so this question is asking, so this question is related to the previous explanation that I gave. If the Fermi temperature of the free electron gas in 3 dimension is increased 4 times, so Fermi temperature is what? kBTF is defined as EF. Okay. So this EF is the Fermi energy. Fermi energy, and we derived that Fermi energy is nothing but h bar square over 2m and 3 pi square n to the power 2 by 3. Now it is saying that the Fermi temperature is increased by 4 times. So Tf initial goes to Tf final, somewhere it is 4 times Tf initial. So you just use the n initial, the number density of electrons, it will go to n final. So how, so it will be just related kbtf initial final is equal to h bar square over 2m 3 pi square and 2 by 3, and this is final, and you just have to divide this expression over kbtf initial is, this is h bar square over 2m 3 pi square and initial 2 by 3. This thing is nothing but tf by tf final, the Fermi temperature final, but Fermi temperature initial, okay, T initial, and this thing is given by nf n final over n initial to the power 2 by 3, and this thing is nothing but tf by t final. From here tf final over t initial is equal to 4, so this thing is 4, so n final over n initial is 4 to the power 3 by 2, so this thing is 4, square root of 4 is 2 and its cube is 8, so nf is 8 times n initial, so it increased by a factor of 8, increased by a factor of 8. Okay, so here what is the key? Here you see we used the formula for 3 dimensions, so that is why use h bar square by 3 pi square n, because this was derived for the 3 dimension. You have to look at the dimensionality as well. If it were asking for some 2 dimensional, then you have to use the corresponding formula in the 2 dimension. Let us go to the next question. Yeah. So here a metallic silver, a metallic silver has this, so this some number, this many conduction electrons per cubic meter. So what it has given is n is equal to 5.89 into 10 to the power 28 conduction electrons per cubic meter, and it is asking the Fermi energy. Fermi energy is EF. Just now we derived EF is equal to h bar square over 2m and 3 pi square n to the power 2 by 3. So you just put your n here, and what you get is the EF, and this EF you will get in joule if you put all the SI units, if you use SI unit. For h bar and m. Okay, so this is how you solve question number 6. For here question number 7, what it is saying, the Fermi energy of a metal, it is given, the EF Fermi energy is given 8.79 into 10 to the power minus 19 joule, and the temperature is given, temperature is equal to 300 Kelvin. Then the ratio of Fermi energy to the room temperature thermal energy. So what is this? Yeah, so we want to calculate what is the room temperature thermal energy. So the thermal energy is defined by as it is the energy by virtue of the temperature, and what temperature it is asking? It is asking at the room temperature. So, and room temperature is given as 300 Kelvin. So it is given as, you simply have to multiply by Boltzmann constant Kb times T. Okay, so the room temperature thermal energy E, you will get when you do kBt, and if you use kb is equal to uh, kb in SI units. In SI units, kb is given as kb equal to 1.38 into 10 to the power minus 23 joule per Kelvin. So if you use this value, you will get energy in joules. But most often in literature and books, you will see energy will be expressed in electron volt. So to convert the energy E to electron volt, what you do is you just divide E by the electronic charge E. This energy E, or kBt by E, where E is equal to 1.6 into 10 to the power minus 19, and you will get this energy in the electron volt. Okay, so when you do that for T equal to so E in electron volt, it is given as kb, so 1.38 into 10 to the power minus 23, temperature is 300 Kelvin over 1.6, E is equal to 1.6 into 10 to the power minus 19. What you get is 0.026 electron volt. Okay, see, it is a very small number, or you can write this as 26 milli electron volt. And this is very frequently used in lot of calculations, so it is good to remember this value, that room temperature thermal energy is 26 milli electron volt. So once you have this, now you can just convert this thing into electron volt as well. So EF can be converted to so you don't even have to convert, you can just either use in kBt. You can take the thermal energy take the ratio EF over kBt, or you can just simply use the values in electron volt, and you will get the values. So yeah, so you have to calculate this quantity, and you will get your answer. Let us go to the next question. So here it is asking, so you are given a solid metal cube of edge length 2 centimeter. So you have been given a solid metal cube of edge length L is equal to 2 centimeter. The lowest energy level for an electron within the metal N metal is N times, so here this N is some integer, okay, some integer or some like some number, not even integer, it may not be an integer, it is some number. So how do you calculate this number? So we have to so to approach this problem, so it is similar to the discussion we did a few minutes before, that we have to think of electrons moving freely in the metallic volume, so one way to solve this is solve Schrodinger equation, and when you solve like in 3 dimension, minus h bar square over 2m del square psi is equal to E psi, and apply the proper boundary conditions, what you get is E is equal to h bar square pi square by 2m L square, and this is nx square plus ny square plus nz square. Okay, so what is this quantity? So nx, ny and nz, this will give you the number of so this is the number which will label your states. So there is one way to easy way to look into what this actually means. So E is equal to, we know that p square over 2m, and E is equal to for P we can write h bar square over 2m into k square. K square is nothing but h bar square over 2m kx. In case you don't want to solve the Schrodinger equation and you want to obtain what is the formula like by yourself, some heuristic arguments. So kx square plus ky square plus kz square. Okay. Now we had discussed that for free electrons in a length L along one particular direction, so this L is given as, so it will have states like this, like this. So basically L equal to n times lambda by 2, like integral multiples of half integers. And now use kx equal to 2 pi by lambda, or lambda equal to 2 pi by kx. So if you just put that, what you'll have, L is equal to n by 2, lambda equal to 2 pi over kx, and k, so 2 cancels 2, kx is equal to n pi over L, or since it is along x direction, you can write nx. Okay, so you put here, so what you get is h bar square over 2m, and you put this thing here, what you get is h bar square pi square nx square plus ny square plus nz square. Okay, so now it is asking what is the lowest energy level of an electron. So what is the value? So to get the lowest energy, what has to be there? So what is the lowest value of n we can put? So n has to be at least 1, because if n is not so n cannot be 0 for any of this. So if along x or y or z, if n equal to 0, that means that there is no electron. Okay, because the states, if you solve the Schrodinger equation, it is given as 2 over L sine n pi x over L, and it is the psi mod square which will give you the probability density of the electrons. So if you put n equal to 0, then psi n mod square, it becomes 0, and that means that there is no electron. So the least value this nx, ny and nz can have is nx. So for lowest energy nx equal to ny equal to nz is equal to 1. Okay, and when you do this, what you get is, it is 3 by 2 h bar square pi square into m L square. So now you have L equal to 2 centimeter, m equal to, so you just put L equal to 2 cm, m is equal to 9.1 into 10 to the power minus 31 kg, and h bar equal to 1.05 into 10 to the power minus 34 joule second, and you will get the value. Okay, you will get the value in so here the value it is asking in electron volt. Okay, so E equal to h bar square by 2m L square. So if you put h bar equal to 1.05 into 10 to the power minus 34 joule second, m equals 9.1 into 10 to the power minus 31 kg, and L is equal to 2 centimeter. So you have to put in SI unit, 10 to the power minus 2 meter. So what you will get is and E is equal to, when you put these values, it is 3 by 2 m L square, and this is h bar square pi square, and you will get this if you put these values you will get E in joule. To convert it into electron volt, so E in electron volt, it will be given by, you have to divide it by the electronic charge. So the 3 by 2 ml square h bar square pi square, you will get some value in joule, and you divide it by the electronic charge. E is equal to 1.6 into 10 to the power minus 19 coulomb. So when you calculate this number, you will have the energy in electron volt, and you can find out what is the factor which is multiplying. So you can find out once you get this value. So this is what you have to do for this particular problem in electron volt. Okay. Now let us go to the next question. So let us again consider a solid metal cube of edge length 2 cm. So what happens to the ground state of an energy of an electron if the dimension of the solid will increase? So dimension of the, so what is the ground state we calculated? The ground state we calculated just before, E is equal to h bar square over 2m l square, and this is pi square, and nx square plus ny square plus nj square. It, like for ground state, it is 3. Okay. So this is your ground state energy for solid metal cube. So it means 3D, like in 3 dimension it is. So this is the ground state energy level. Ground state energy level. So what will happen if the dimensions of the solid, dimensions means the only dimension of the solid is coming into play here. So L is the dimensions of the solid. So the ground state energy is inversely proportional to the square of the dimension. So now if the dimension will increase, if L will increase, then E, since it is inversely proportional, E will decrease. So therefore it will decrease. So now here it is like for a free electron. So for a free electron gas in 2 dimension, the density of states is given by. So this you can find out using the technique which I told earlier. So basically you have to the density of states and L. So what you have to do, basically you just have to put 2 pi now whole square and dkx dky and 0 to infinity, 0 to infinity, and then you use the dispersion relation. Use dispersion relation h bar square k square over 2m after you convert this to a radial coordinate. So this is in Cartesian system, convert to radial, and then use this dispersion relation and use an L over L square. L square is this area, and you have to multiply with spin. Is equal to GE 2D over DE. Okay. So if you follow the previous slides, you can easily able to find what is the GE 2D. So this was there in your assignment. So week. Okay. So this is question number 10. So this was for this was the assignment 1 of the last week. Last year. We can go to have a discussion on the practice assignment week 0. So here the question it is asking is, which of the following is the effective mass if the energy wave vector relation? So energy wave vector relation is given, E is equal to some h bar square k square over 3m. The way we calculate the effective mass is, so effective mass is defined as E equal to h bar square k square over 2m effective. So this is the general dispersion relation, and if we do, let's say, first derivative, dou E over 2k, so h bar square k over m effective, and if we do a double derivative, dou 2E over 2k square is equal to h bar square over m effective. So m effective is equal to nothing but h bar square over the second derivative of dk square. Okay. Now you have been given, so the energy, so this is a general formula. like which is quite often used in a lot of problems. So you use this expression for use this expression in here, and you will get the relevant formula. So E equal to h bar square k square over 3m. This implies, so d E by dk is equal to 2 h bar square k over 3m, and if we do the derivative again, d2e over dk square is equal to 2 h bar square over 3m. Now you just put it over here, so m effective, so if you put it over here, it will be so it will come out to be 3m over 2. So this is your answer. So here it is. The next question, what it is asking? It is asking the first excited state of a free electron in one-dimensional infinite well potential. So it is asking about, again, one-dimensional infinite well potential, which we talked about a few minutes before. And what is the first excited state? So E is equal to the same technique that we will use, E equal to h bar square. Since it is one dimension, we can just write k square over 2m. And here it is asking about the first excited state. First excited state, so the ground state is this. First excited state is this one, 0 to L. So basically L is equal to lambda. Okay, so lambda is this whole wavelength is there. So k is equal to 2 pi by lambda, or what it will be. So k is and lambda equal to, lambda is L. So it is 2 pi by L. So you just put this value of k here. So h bar square over 2m, k will be 2 pi by L whole square. So it is 2 h bar square pi square over m L square. Okay, so this is your first excited state. Or and if you remember the formula, the general formula is h bar square pi square n square over 2m L square. And for ground state, n equal to 1, ground state, and for first excited state, n equal to 2. Okay, so the graphite is a good conductor of electricity. So this is another question which is asking, graphite is a good conductor of electricity due to the presence of so a lone pair of electrons, valence electron, cations and anions. Okay, let us see what is the case. So we have to look at the structure of the graphite. The structure of the graphite is actually two-dimensional, and so it is nothing but carbon. The carbon atoms are arranged in hexagonal shape like this. So it is a 2D infinite set. And let us look at the electronic configuration of graphite, or the carbon in graphite. So carbon has 6 electrons, and those 6 electrons are distributed as 1s2, 2s2 and 2p2, or basically 2px1 and 2py1 and 2pz, and it will have no electrons. So this is the electronic configuration of one carbon atom. But here you see this carbon has the carbon in the graphite, it has like a kind of symmetry here, and it has 3 longitudinal orbitals like this. So why this thing happens? This thing happens because of something called hybridization, and this thing is sp2 hybridization. So in sp2 hybridization, what happens? For each carbon atom, so in the plane of So this is a 3D diagram. You just try to imagine. So this thing is this is coming out. This is coming out of the board, and this is coming into the board. So these three are the sp2. So sp2 have sp2 orbital will have these three loops like this: 1, 2, 3. Okay, and there is one another orbital which is pz, which will be on the board, which is like this. Okay, so this is the electronic configuration. So this is sp2, one lobe of the sp2 orbital, this is another lobe of the sp2 orbital, and this is another lobe of the sp2 orbital. These three will be like, for example, this carbon you take. So this is on the plane of this on the screen. So this thing is these three orbitals, and another orbital which is like one lobe coming out of the screen and one lobe going into the screen. So that is another orbital. So in that orbital, so these three will take 3 electrons: 1 electron, 2 electron, and third electron, and one more electron will go into this pz orbital, which is not hybridized. Okay, so in sp2 hybridization, so you see that valence, this 2 has 1, 2, 3, and 4. So out of these 4 electrons, each of these bond sp2 orbital will take one electron, and one electron will be there in this unhybridized orbital, and this is the free valency electron which will contribute to the conduction of electricity in graphite. So you can imagine this as like these two lobes, which is one going into the screen, going out of the screen. For this carbon also there are 2 lobes. So this electron, so there are electrons here, it can move around along the surface of the graphite. So that is why graphite is a very good conductor of electricity. Yeah. So now another question, what it has given, the tight binding dispersion relation E of K, it is given as A naught plus A sine square K A by 2, where E naught and A are constants and A is the lattice parameter. Okay, what is the group velocity of an electron? It has already given the formula of group velocity. So what you can do is you just simply put the value of energy here and do the derivative. So I just want to tell you how what motivates this expression for Vg. So we know that a velocity like p by m, the momentum by the mass, it has the expression of this velocity, right? So from energy E is equal to p square over 2m, and if we do dE over dP, what we get is p over m. Okay, and p over m is nothing but your velocity from here, and p you can write as, so v is equal to, so from here we just get dE over dP. Okay, p if you put h bar k, so dP you can, so, and h bar is a constant, so it is 1 by h bar dE over dk. This is your velocity or the group velocity. Now you just do the derivative. So dE over dk is equal to, A naught is a constant, it goes away. So so 2 sine k A over 2 into cos k A over 2 into, since and there will be an A by 2. So this thing will be nothing but dE over dk is equal to A by 2, and see 2 sine k A by 2 cos k A by 2. So you can use this identity, sine k A by 2 cos k A by 2 equal to sine k A. So so it is just 2 sine x cos x equal to sine 2x. So it is just sine k A. Okay, so the group velocity will be A by 2. So there should be some 1 by h bar factor. sorry. So it is AA by 2 and sin Ka, AA by 2 sin Ka. There should have been one H bar factor, but so this is the closest to the expression. So we'll go to the next question. So here it is asking that assuming that the conduction electrons in copper behave as a classical gas. So when we talk of the classical gas, so it just means that the electrons in a classical electrons are the particles in a classical gas. They follow something called Maxwell-Boltzmann distribution. Maxwell. Okay, so this is what it means by classical. So the Boltzmann distribution, or it is like e to the power a over kt. Okay, the probability that you will get a particle of energy E is directly proportional to this. So this was what in the classical picture. But when we incorporated the quantum ideas, this became the Fermi Dirac function. So that is when it would have asked the quantum gas, then we would have used a Fermi Dirac function. But since it is asking classical gas, so we have to consider this. And a consequence of this, so since it is like free classical gas, so E will have nothing but half mv square, just the kinetic energy over kT. The consequence of this is that like there is something called equipartition theorem. Equipartition theorem. For each degree of freedom, you will get for each degree of freedom of energy, you will have a contribution of half kBt. Okay, so that is a consequence of following this Maxwell-Boltzmann distribution. So what we have is, so you want to calculate the speed. The speed is nothing but half m. So the thermal energy E of the electron, thermal in the classical picture, is half m Vx square plus Vy square plus Vz square. So the speed V is given as Vx square plus Vy square plus Vz square to the power 1 by 2. So the speed, so this will give me the speed. So from the equipartition theorem, what I have is half, so each of this energy, so half m Vx square. So this is 1 degree of freedom for the energy, half m Vy square, this is 1 degree of freedom for the energy, and half m Vz square, this is another degree of freedom for the energy. And each of this will give me each degree of freedom of energy. So energy which is quadratic in nature. Okay, so here Vx square, it is quadratic. So this will give me contributes kBt, half kBt of energy, thermal energy. Okay, so this 1 by 2 kBt plus 1 by 2 kBt plus 1 by 2 kBt. So and this is 1 by 2 m. So V square is equal to this. This is nothing but 3 by 2 kBt. So from here you will get like half m V square equal to 3 by 2 kBt. So V is equal to 3 kBt over m and its square root. Okay, so you put this formula, T it is given 300 Kelvin, mass you have to put, since it is electron, mass equal to 9.1 into 10 to the power minus 31 kg. Minus 31 kg, and kb is the Boltzmann constant. You just put and you will get the velocity in SI unit. So the next question, it is asking about an n-type semiconductor from silicon, and it should be doped with a substance with the number of valence electrons equal to. So for A silicon is a valency 4, it has valency 4. So silicon will have 4 bonds, okay, 4 bonds. So silicon, this will have again 4 bonds, 1, 2, 3, 4. Some silicon here, it will have 4 bonds. Silicon, it has 4 bonds. And each of this will have shared 2 electrons, okay. So each of this will have 2 electrons, this will have 2 electrons. So if you want an n-type semiconductor, so for an n-type semiconductor you need an extra electron, and if you dope with something of, let's say, valency 5, so so you need to bond it with something which has a greater than the number 4, okay, which has the valency electrons greater than the number 4, which is 5. So that is how you will have this extra electron. So for example, it's a phosphorus, so it will bond with 4 of this silicon, but there will be an extra electron which will be just lying around, and this will contribute to this will make the semiconductor an n-type, okay. So that is why you have to dope with a substance with a valency electrons equal to, which is greater than 4, okay, greater than 4. So the next question here, the potential difference of a diatomic molecule as a function of R. So the potential difference is given, the value of potential at equilibrium separation, okay. So we have to find what is the equilibrium separation. So to get the equilibrium, so what do we mean by equilibrium? Equilibrium in which the force is 0, and the force, it is given by force is minus dou V over dou R. So, or since it is just a function of R, so d by dr of V, okay, and we want to put it as 0. So this is nothing but dV by dr is equal to 0. This will give me, so you just put d by dr of minus a over r6 plus b over r12 is equal to 0. This will give me minus a minus 6 by r7 plus minus 12 v over r13 is equal to 0. So this gives me 6a into r6 equal to 12b. This implies r6 equal to 2b over a. So at the equilibrium separation, or r equal to 2b over a to the power 1 by 6. So this is equilibrium separation. The separation at which the force equal to 0. So at this, what is the value of potential at this value of r? So you have to put V of r equal to 2b over a to the power 1 by 6. You just put that. So minus a r6 is equal to 2b over a plus b over r12. So it is 2b over a whole square. So it is minus a square over 2b plus a square over 4b. So it is minus a square over 4b. So this is your answer. So the next question is, what is the percentage of empty space in a body-centered cubic arrangement? So a body-centered cubic arrangement is, you will have a cube, and so on each of the corner you will have a sphere. So this sphere, okay, on each of this corner you will have a sphere, and there are two more spheres which are like inside, which is not visible, and in the body you will have a sphere which is at the center. So a body-centered cubic arrangement, so what you have to do is actually fill this diagonal with sphere. So if you consider the diagonal, So let's say this is the diagonal of the cube. So the diagonal of the cube has to be in, so this has to be completely packed. Okay, so if you have this as the diagonal, the length of the diagonal will be 4, so this is 1r, this distance is 2r, and this is 1r. So 4r equal to length of the diagonal, length of diagonal. And the diagonal of a cube is, so it is a square plus a square plus a square 1 by 2. Okay, so this is length of the diagonal. So this is basically root 3a. So root 3a, where a is the side of the cube. Side of the cube. Okay, so the number of spheres in this body-centered cubic arrangement, number of spheres in BCC arrangement. So one comes from the, so one sphere is in the center, which is you can count it as 1, and there are 8 cubes, and each of from this 8 spheres, 1 by 8 the volume 1 by 8 of each sphere is there. So it is 1 by 8 times 8. So basically there are 2 spheres in a unit cell. So you want to calculate what is the empty space in the body center. So empty space will be, empty space in BCC will be how much? The volume of the cube, volume of cube minus volume of spheres, and we want to find in the percentage. So basically you have to do volume of cube, and since it is, you have to express in percentage, you have to do this in percent. So it is 1 by volume of spheres. Volume of sphere will be 2 times 4 by 3 pi r cube, and volume of the cube is a cube. Okay, and so what you have to do is, you have to find r by a whole cube. So r by a cube, from this expression you will get root 3 by 4 whole cube. Okay, you just put this and you will get and this has to be multiplied with 100. So when you put this r by a whole cube, you will get around around 32%. Okay, so you just have to put this value in here, the value of r by a. Okay, so the next question is, what is the coordination number in a square packed structure in 2 dimension? A square closed packed structure is given, square closed, it is just like imagine a sphere here, a sphere here, a sphere here, and then a sphere here. So this is a square closed packed structure. Okay, and the coordination number means so for a given sphere, what are the how many number of other spheres it is connected to, okay, or it can coordinate with. So it is just 1, 2, 3 and 4. So this will be your answer. Okay, 4 neighboring. Which of the following statement is not true? Okay, the paramagnetic substances are weakly attracted by the magnetic field. So the definition of paramagnetic substances are that, so paramagnetic substances have a magnetic susceptibility which is proportional to the magnetic field. So basically it means that they get attracted to the magnetic field. So this is true. Okay, ferromagnetic substances cannot be magnetized permanently. So this thing is false. Why? Because uh, so ferromagnetic substances are those substances in which, so if we remove the magnetic field also, the magnetization will still be there. So that is why, so it is the definition of ferromagnetic. So this thing is false. Uh, it can be actually permanently magnetized. So the permanent magnet that we see, those are ferromagnets. So there are some other class of substances called antiferromagnetic substances, in which uh, the domains in the antiferro are oppositely oriented with respect to each other. Yeah, so there is domain. So for example, we have a magnetic substance. Okay, so there are certain regions in which the spins are aligned uh, with each other. Like for example, if we see a particular region here, all the spins will be aligned in one direction. Uh, but for antiferromagnetic substances, what happens is, so the domains, so there would be domains in which they will be oppositely aligned. So this is a true statement. And a pairing of electrons cancel the magnetic moments in diamagnetic substances. So those substances, so the spin of the electrons is actually contributes to the magnetism in the materials. Okay. Uh, in diamagnetic substances, what happens? The electrons pair, and the spin up and spin down, they cancel, and the magnetic moment, it will be cancelled. So this is also true. So this is the only not true sentence. Okay. So these are your these are the assignment questions of the last year, week 0 and week 1. And using these concepts, you can solve the present year questions as well. And if you have any doubt, you can if you have any doubt in any question, you can ask me.
Sir, good evening, sir. If you are considering any bar of that temperature, at one end it is cooler and another end it is warmer, how to calculate the temperature, sir? So that means, can we
Okay.
take the
Yeah.
equal intervals like that?
Yeah. I'll just explain how that thing can be approached. Suppose so there is this thing called Kirchhoff's law. Kirchhoff's law of conduction of. So what happens is, suppose if you have a bar, or let's say in general, you have some material, okay, and it has, so you want to find, so it has a length L1 and it has a length L2, okay, and it is at temperature T1 and it is at temperature T2. You want to find what is the temperature T here. Let's say this is made up of a substance which has a thermal conductivity K1, and it is made up of a substance which is made up of a thermal conductivity K2. Okay, and you can also assume that it has a cross section area A2 and it has a cross section area A1. Okay, so because of this temperature difference, what will happen is, uh, because of this temperature difference, so let's say T1 is greater than T2, then heat will flow from here to from T1 to T2. The point to note is that heat will not be accumulated at a particular point. Heat is flowing. Heat will not be accumulated. Now you see the heat passing per unit area per unit time uh, in this bar 1 will have to be same as, so if it is going like this and here it is going like this, okay, the heat is going.
Or if we are considering the same bar, sir, suppose we are able to take some bar of length, let it be as 1 meter, something like that one. Then
Yeah.
automatically one end is at some temperature. Anyway, we have to satisfy the condition. T1 must be greater than the T2.
Yeah.
At
Yeah, I'm
some,
coming to
at,
that.
yes.
Yeah. So this is what So this thing has to be kappa 1 delta T over L1, right? So delta T is like you just have to put T1 minus T1 is greater, right, over L1, right? So this has to be equal to what is the heat going through this. This has to be how much? So basically Q by T is equal to K1 A1. So this is the condition you have to satisfy, and this has to be equal to K2 T2 minus T over L2 into A2. Okay. Now imagine that you have the same bar and same cross section area.
Yes,
So
sir.
if you have same cross section area, A1 will be equal to A2, right?
Yes.
And K1 will be equal to K2.
Okay, sir.
You got it right? Then what
Yes,
will
sir.
be for same?
T1 minus T by
Yeah.
both the length is also same.
Huh. For like if see, if it is, let's say, for same bar, if it is
Hmm.
asking, let us go to this question. So if you have this bar, okay, bar of same material, bar of same material. So the K1 will be equal to K2 and A1 will be A2 and same cross section. And you are asked to find somewhere around here, okay, L1 and L2. L1 need not be equal to L2, okay. It can say that
Oh.
the total length is L. You find at the fraction 0.2 of from the this end, okay, from end A, from
Oh.
end 1, okay. Then what you have to do? So T1 minus T, so this is T1, T2, T1 minus T over L1 is equal to T2 minus, sorry, T1. So this has to be at greater temperature, no? So T minus T1 over L1, T2 minus T over L2. Understood? So now if you solve this, so T minus T1 is equal to L1 by L2 T2 minus L1 over L2 T. So basically you will find T will be equal to T2 L1 over L2 minus, sorry, plus T1 over 1 plus L1 over L2. So basically you can find it out from here, right?
So that means L1, whatever the L is the total answer. L1 is at point where to measure, or total length minus that point. Suppose I need to find it as at point 2 meters.
Here at point 2, right? You are giving L as 1 meter.
Okay. L2 is, sir,
L2 is the distance from this end,
point 0.8.
from
Yes,
T2 end. Okay?
point 0.8.
Yeah.
Okay.
So,
And T is temperature is capital T means
yeah, capital T is the temperature at this junction.
capital T is the temperature at. Oh, okay. We have to find that cap. Okay, sir. Got it. Thank you.
Yeah.
And one more doubt, sir.
Yeah.
As you said that one, according to that Weidemann Franz law,
Haha.
that is kappa by sigma directly proportional to the temperature. No, sir. According to that one,
Yeah.
that means conductivity is the ability to conduct the heat is directly proportional to absolute temperature.
Absolute temperature, yeah.
And then is that it will be affected by the electrical conductivity also?
Say, thermal conductivity is, so say, there is a temperature dependence in sigma as well. You
Yeah,
understand?
okay.
So you cannot directly say that the thermal conductivity is directly proportional to temperature. You cannot say this because there is some temperature dependence here. Okay.
So
So
that means
it,
thermal conductivity is definitely it will be affected by temperature and electrical conductivity
yeah,
both.
exactly. So if you want to find the temperature dependence of the thermal conductivity, then you have to find this expression. So this is the Weidemann Franz law of
Weidmann
temperature.
constant
So
as you
sigma,
said.
and this sigma you have to express it as a function of temperature. Okay.
Function of
And
temperature.
the way you have to do is this is, sigma is equal to n e square over m tau, right?
So that means
Uh,
that thermal conductivity is affected by both electron density and also temperature, everything.
yeah, it is dependent on the material properties which come into picture is this electron
Uh,
density. Okay.
okay.
And another thing, this tau is
Relaxation.
dependent on the temperature.
Okay, sir. Yes, sir. Yeah,
Okay.
because M by N is like that one. Yes.
Yeah.
Okay, sir. Okay. And last and final doubt, sir.
Yeah.
So, as you already explained in that seventh bit, like that one. So
Okay.
that means while we are calculating that one Fermi energy, sir.
Which one?
So Fermi energy,
Which question you are saying?
seven, sir, seventh bit.
Seventh bit. What is the question? Can you
In
repeat?
assignment one, seventh bit in an assignment one, that Fermi energy is equal to 8.79 into 10 power minus 19 joules at room temperature is 300 K.
Okay,
Then
okay, okay.
thermal
Ha ha.
energy
Ha ha.
is equal to kBt, no, sir.
Ha.
And while we are calculating that one electron volts, I got that one, whatever your explanation. So
Okay.
if you want to find the ratio of Fermi energy to thermal energy,
Yeah.
then can I take that one directly like EF by K?
No, you have to find this EF by KBT. Okay. Here, whatever, what is the expression that is given in
For once,
your
if it is
expression?
possible, can you show me that bit?
Okay, just a second. Question number 7, right?
Yes, sir. Question number 7.
This one.
Yes, sir. That's it.
Huh.
Yes, sir. Fermi energy to room temperature, sir.
Fermi.
Room temperature thermal energy means how you took this one.
Oh, okay. Room temperature thermal energy is you just have to multiply Kb with this temperature, with the room temperature.
Okay, sir.
Okay, Kb you put this value 1.38 10 to the power minus 23 and T you put 300.
Um, okay, sir. So that means whatever the Fermi energy of a metal they are giving, we may not took it directly. So definitely we have to take like this one. It is a KBT.
See, so there are two different quantities here, okay? For a metal, so Fermi energy is a material property, okay?
Okay.
It is the property of the metal,
Okay,
okay?
sir.
It has been given. Uh, Room temperature thermal energy, it is a different quantity,
Okay,
okay?
sir.
It is not related to the metal, okay?
Okay, sir. Okay.
So it has asked you to find, so it has given this, it is asking you to, so you have to find basically ratio of EF and the room temperature thermal energy. So you have to
O-
find room temperature thermal energy. How do you find that? It is just this expression.
Okay, sir. So coming to that assignments, if they gave something like a blank, then it is not accepting that one, that letters. The energy obviously it has to be expressed in electron volts. So that means default is it will take in electron volts.
No, no, it will not be in any unit because it is a ratio.
No, sir. No, sir. 1 minute, sir. Sorry for the interruption.
Yeah,
Sir, if it is like an options, it is okay, sir. But if the bit is given like this or something like this one,
yeah, yeah. Okay,
like
I'll tell you.
similar bit like this, one blank page given like this one. In that box, it is apart from that numbers, it is not accepting in order to write electron volts and all.
You don't have to write that. I understood your question. Say, what you have to do, just a second. Huh? Just new slide. So it is a ratio, okay? So you have EF, right? EF equal to how much it
Yes,
is
sir.
given? Some value, let's say I'm just putting some arbitrary number.
Yes, sir. Okay.
Some arbitrary number, okay?
Okay.
You get it from the question.
Yes, sir. Okay, sir.
Arbitrary number.
8 point. Okay.
Let's say I'll put some 10 electron volt, 10
Okay.
joule. It has given joule, right?
Yes, sir.
Okay.
10
So,
joules.
and temperature equal to 300 Kelvin it is given.
Yes,
300
sir.
Kelvin.
Okay.
So, thermal energy,
KBT, that is
thermal energy,
1.38.
the way you have to do is E thermal is equal to
Okay.
kBT. kB is what? 1.38 into 10 to the power
10
minus
power minus 2.
23 joule per
Okay.
Kelvin. Okay.
Okay, sir.
T is
Okay.
what? T is 300
T is
Kelvin.
300 K.
Okay. So you will get a number
In joules.
in joule. Okay.
Yes, sir.
So this is your E thermal. You have to find EF by, you have to find a ratio, right?
Yes, sir.
Thermal. Okay, so this is, let's say 10 joule over,
Oh,
this is some number joule.
okay.
This joule cancel. So what you
Okay.
have is
Ratio
a,
will be a fine number. Okay.
it is a
Thank you,
number.
sir. Now I got it.
Yeah.
And thank you, sir. Thank you so much, sir. One request: can you share me like whatever that calculations, because there is a vast derivation for that density of states in
Yeah,
that
yeah,
one.
okay, yeah. That will be sent in a link. So I think it will be shared with you also. uh, how do I share this one? Just
Yes,
a
sir.
minute. There
Is
is,
it will be in recording mode, sir? Or
yeah, these things are recorded,
okay.
and just stop. Yeah, yeah. If anyone has any other doubt, they can tell me.
Thank you, sir.
Yeah. Uh, so this thing will be recorded and given to you. Okay. So
Okay, sir.
anyone other have some other doubt? Then we can close the session. I'll just